So on page 22, we have example 4. We have a cylindrical can that's going to be designed, and it's going to hold 384 milliliters of soup. Well, that's a constraint. Looking ahead, if we want to minimize the cost to build the can, we obviously don't want a can that has 384 milliliters of soup and then a whole bunch of empty space. Okay. Aside from bacterial problems with that, we want to make sure that the can is full of the soup so we're not wasting material. So this is a constraint. And we can label the constraint mathematically by saying the volume has to be 384 cubic centimeters. Now, in terms of fluid measures, a milliliter is a cubic centimeter. So that's the equation of, well, that's not the equation of constraint. We haven't got an equation for it yet. I guess to get an equation of constraint, we have to take the volume formula, which is pi r squared h. So V is equal to pi r squared h. Which means pi r squared h is equal to 384. Now, how do I know the volume of a cylinder is pi r? I don't know why I wrote over h. How do we know the volume of a cylinder is pi r squared h? Well, I suppose you can, I have to fix this. I suppose what you can do is just go to a formula sheet, but I think it's very useful for you to understand why it's pi r squared h. And the reason is that a cylinder is a uniform, regular solid. When you take a look at a cylinder, and you talk about the shape of the base of the cylinder, the shape of the base is a circle. And if you talk about the shape here, it's a circle. And you talk about the shape on the top, it's a circle. And it's the same circle everywhere. So we've learned that the volume of a regular solid is found by taking the area of a base. Well, the base of this is pi r squared for an area times the height. So that's the equation of constraint. So now we have to develop a formula for the thing we want to optimize. Well, we want to optimize, we want to minimize the cost of materials. And with this example, we're making a big assumption here that the cost of the material for the top and the bottom of the can is the same per unit area as the cost of the side of the can. You're going to be getting an assignment either tomorrow or Friday where you have to minimize the cost of a barrel, but the top and the bottom materials for the barrel cost different amounts of money per square foot than the side of the barrel material costs. So you would have to take that into account. What you need to, I guess, appreciate here is that the cost is representative of the surface area. We don't know how much the material costs per square centimeter, but it doesn't matter. If we make the surface area as small as possible, whatever the cost per unit area will be as small as possible for a total cost. It doesn't matter how much it is for each little piece. If the total of the pieces are smaller, then the cost will be smaller. So we're going to come up with a formula for surface area. I've always disliked writing S dot A dot for surface area because it's no longer a variable, it's an abbreviation. So what is the area of a can? If you were to go to your formula sheet that I've provided with you, the formula is 2 pi r squared plus 2 pi r h. Now, just like I explained where this formula comes from, I'm going to explain where the surface area formula comes from. And the reason for that is, if you're doing post-secondary math and you have an exam, they're not going to give you these formulas. It's very unlikely that they'll be given to you. The first thing to note is that if you were to take a look at a cylinder, the top of the cylinder and the bottom of the cylinder are circles. So this is the top and bottom. If I said, what's the area of the top? You would say the area of the top is pi r squared. What's the area of the bottom? Pi r squared. I know I said those in opposite orders, but you get the idea. The area of the top is pi r squared. The area of the bottom is pi r squared. So we have 2 pi r squareds. Now, why is it that this is the area of the, quote, side of the cylinder? Well, if you don't do this unless you're going to tape the label back on, but if you go to your pantry at home or your cupboard and you take out a can and you very, very neatly take a knife, a sharp knife, and you cut the label from top to bottom. Now it's going to be glued someplace, but then what you do is you unwrap this. You pull that away and you pull that away. What you're going to get is a rectangle. It shouldn't be any surprise that you get a rectangle. When you peel the label off, it's not going to be a circle or anything. It's going to be this long rectangle. And I have an animation I will show you in a second, but it's going to be this long rectangle. And the dimension of the rectangle vertically is the height of the can, and this is the circumference of the can. And the circumference of the can is 2 pi r. So if you wanted to find the area of this rectangle, you would take 2 pi r, which is the length, times the height of the cylinder, which is the width. And that's where that 2 pi r h comes from. Looking at it visually, it's going to reset in a second. There's your cylinder with the height. You peel it apart to get a rectangle. The circumference of the circle is the actual length of the rectangle. So what you end up with is 2 pi r squared for the 2 circles, and you have length times width for the label or the side of the can. So that's where that formula comes from, and I hope that helps you so that you can come up with it on your own. What's the problem here? The problem is we don't have only one variable on the right-hand side. I would like to eliminate either r or h from the right-hand side, and I believe it's going to be simpler to eliminate h, and I hope you would agree, simply because h only appears in one place. The other thing is, when I eliminate a variable, I take my equation of constraint and I rearrange it for the variable I would like to eliminate. Now stop and think about this. If I wanted to eliminate r, then I would have to rearrange my equation of constraint for r, and that would mean introducing square roots. And I think I would rather not work with square roots than work with them. So this is what I'm going to put in for h. All right, so this h here is going to change into 384 over pi r squared. Now I have the area, surface area of the can, which is representative of the cost, is 2 pi r squared, plus 2 pi r times h, which is 384 over pi r squared. Of course, you want to simplify always before you differentiate. Just checking my substitution, it looks fine. So simplifying this, the surface area, which is representative of the cost, is 2 pi r squared plus, can somebody confirm that 2 times 384 is 768? Good. The pi's cancel. We have a pi on the top, and we have a pi on the bottom of that expression, of that term. And I have an r on the top and an r squared on the bottom, so I end up with over r, which for differentiation purposes, I'm going to write as r to the negative 1. So for this can, if you wanted to design a radius, a can with a radius of 1 centimeter, which is really a goofball move, then you could put 1 in for r in this equation, and that would give you the area required. So think about, you know, a regular size soup can, which is 384 milliliters, and you're going to design a can with a radius of 1 centimeter. So the diameter is going to be 2 centimeters. What would the surface area be? We don't need to do this to answer the question. I'm trying to get you to think. The surface area would be 2 times pi times the radius, which is 1 squared, plus 768 divided by the radius. 2 pi r squared plus 768 over r. It would be 774 square centimeters. It would be this can that's very, very thin and incredibly tall. On the other hand, let's say that you wanted a can whose radius was, let's say you wanted a can whose radius was 85 centimeters. So that's just the radius. If you double that, you get the diameter. We're talking about a can with a diameter of 1.7 meters. And it's going to hold 385 milliliters of soup. It's going to be a very short can. The height of this can is going to be incredibly small. The area, which is representative of the cost, would be what we get when we take 2 times pi times that radius squared plus 768 divided by that radius. Huge, huge, huge surface area in terms of square centimeters. What we're after is the optimal radius that will minimize the can's area. So we differentiate. dA dr is equal to 4 pi r minus 768 r to the negative 2. So everybody just ponder that step and make sure you're fine with differentiating the area function to get dA dw. dA dr actually, sorry. I'm fine with it. I'm assuming that 4 divides into 768. So I can factor a 4 out. And I factor out r to the lowest exponent. What's that going to give me out of the first term? Well, I take out the 4 and I leave the pi. And I take r to the negative 2 out of r to the 1, which will give me r cubed, minus I take 4 out of 768 and get, I need some help here, I just rolled that around in my head, but I believe you get 192, and it is 192, thank you, Dan. And I took out the r to the negative 2. So my derivative is dA dr is equal to 4 times pi r cubed minus 192 over r squared. So we've got a couple of critical values of r. One of the critical values of r for this derivative is 0, because that would make the derivative undefined. And one of the critical values of r is the cube root of 192 over pi. So I suspect that many of you can merely look at this and see that it's the cube root of 192 over pi. But in case you can't and it's not obvious, what we're doing is we're asking ourselves where pi r cubed minus 192 equals 0, because then the derivative would be 0. I add 192 to both sides. I divide both sides by pi. And that leads me to taking the cube root. So of these two critical values of R critical equals 0 that's crazy talk. Because you want a can, you have to have a can to put the soup in. By the way, if the radius was 0, the height of the can would be infinite. So what we've discovered is the radius of the can that will produce the least area, which is the least cost. What was the exact question here? It says, what are the dimensions of the can? Okay, so the dimensions of the can are going to be the radius and the height. We still have to find the height. This is the radius. What's the height going to be? Well, we're going to use our formula for height that we developed. And I believe, but again, I want to keep you focused and involved so you can just double check that it was 384 over pi r squared was how we got the height. Is that correct? Okay, so I'm going to put in the radius. Now this is going to get pretty ugly. So what I'm going to do when I put in the radius is I'm going to put 384, and then I'm going to go over pi. And for the radius, I'm not going to use the cube root of 192 over pi. I'm going to put the cube root of 192 over the cube root of pi. So I have a complex fraction here, but that's okay because I have pi to the 1 on the top. Let me rewrite it with exponents. We have 384, and I have to square this, by the way. So I'm going to put the squareds here and here because it's pi r squared on the bottom. So I have my pi. I'm going to write the 192 cube root squared as 192 to the 2/3. I'm going to write over pi to the 2/3. Then what I can do is take the pi to the 1 over pi to the 2/3. I can subtract the numerator exponent of pi minus the denominator exponent of 2/3 pi and get a third pi. How important is all of this? Well, not really important. We could just go to decimal form at this point, but I wanted to show it to you. So the height in simplified form is 384 over pi to the 3rd times 192 to the 2/3. And I don't think you need to simplify any of those further. Could you write these in radical form? Without a doubt, of course you could. What I would like you to, well, I'll just pause there. Any questions with that last step? What I would like you to do is calculate the decimal values of r and h. Before you do, once you get the decimal value of r, just put it in here to find h. Don't worry about putting it in that 384 over pi to the 3rd, 192 to the 2/3. I'm going to do the same thing as well. Just in case you need to look at the calculator work here and you need some help. I don't generally use the cube root function. I just say raised to the 3rd. This is what I'm getting for the radius of our can. And if you were to take a look at the height, I have to take 384. I have to divide it by pi. And I also have to divide by the radius squared. So these are the numbers that I'm getting for the radius. 3.93 centimeters by 7.88 centimeters. Now I just want to discuss something briefly because, and I never did this until a few years ago, a student came back to me the next day and they said when I went home and I measured the dimensions of a can, of soup, those weren't the dimensions. And he was right. They're not the dimensions because in reality, the top and the bottom of the can are more expensive to produce, and that affects the results. Anyway, any questions with that example? Okay, let's take a look at the final example. And the final example I can teach to you, in a very simple way, and we can just work through it and it makes sense. But I have a feeling that I would be shortchanging you in terms of post-secondary, because if you did what we are going to do in post-secondary, you might not get full marks on your exam or your assignment. Let's dissect this question first of all. We're going to build a rectangular rec hall on the shore of a lake. And what we want is one of the walls to be made of glass. And the reason why we want one of the walls to be made of glass is we want the wall that's facing the lake to be something that students can look through and watch the lake. So the bottom line here is we have a rectangle we're going to construct. And we're going to want to minimize something. I'm not quite sure which way this is going to land, but I'm going to say the lake in our diagram is over here. So on my diagram, what we've got is a wall that needs to be made of glass, and then this wall is going to be brick, this is going to be brick, and the other long wall is going to be brick. And the problem in this question is what dimensions will minimize the cost. So normally what I would say to you is that the cost is representative of the perimeter. And we're going to write this down, and then I may decide to add some other things and talk about post-secondary. But if I were to call, I'll use a different color so you can see it better. If I were to call the length of the wall facing the lake L, that would mean the length of this brick wall is L, and I would need to call the length of this brick wall W and the length of this brick wall W. And very similar to the can question, we would start by saying that really, you know what? It's the perimeter of this building that represents the cost. Because if all of the walls are longer, it's going to cost more. And I would like you to be very careful on how you write this down. The perimeter is representative of the cost, and it's going to be equal to W plus L plus, and I want you to leave some space here before you write your other L. Now, since the glass wall has a different cost per foot of wall, it should be weighted differently. And the cost per square foot of the glass is 3 times that of the brick. So although this is a perimeter, if we want it to be truly representative of the cost, we need to multiply that length by 3. And what we end up with is that the perimeter that truly represents the cost is 2W plus 4L. Now, this is where if you were in post-secondary, somebody marking your work would say, well, we're not minimizing the perimeter, we're minimizing the cost. So if you look at this question here, it says ignore the thickness and height of the walls. We understand that these walls have a height to them that we're not seeing here. But the building walls are the same height everywhere. So if I were to include the height as part of my cost calculation, there would be a constant being multiplied to every term. And the derivative of a constant times a function is the constant times the derivative of the function. So we don't need to worry about that. It's the same with the thickness. But if you truly want an equation that takes cost into account, you would have to know, I'm just going to say that this is 1 foot. Are we in feet in this question? Yes, this is 1 foot. You would have to know the cost for 1 foot of wall. But let's say the cost for every foot of wall was, I'm going to say $40. If the cost was $40, we'll go with brick, $40 per foot of wall. That means a foot this way. So that includes, the cost is included in the height of the wall and the thickness of the wall. That would mean the glass would be 3 times that would be $120 per foot. So what would your equation for cost be? Well, your equation for cost would be W times 40 plus W times 40 plus L for the brick times 40 plus L for the glass times 120. So your actual cost formula would be 80W plus, I believe, 160W. Notice, however, that if I find, I won't even talk about the derivative. Notice, however, that if I factor out a 40 out of this cost function, I get 2W plus 4L, which means the variable part is what's important. So this is why we're able to cheat the system and not actually do cost. The question that some of you are going to have rolling around in your head is, can you do it this way on the right? Well, you could if you knew the cost per foot. If you don't know the cost per foot, then in post-secondary you can't put the number 40. You have to put something for a constant, like R. And you would have an R here, and an R here, and an R here, and a 3R there. But then you could take those R's out because they're just constants and not variables. My intention in doing this on the right is not to confuse you. If what I have on the left is understood by you, then I've achieved my goal. If some of you that are going to go to post-secondary maybe remember our discussion about actual cost functions, then I've also achieved my goal. But if you don't, I haven't failed. So going back to this idea that the cost of the brick is 3 times as much, which leads you to this term, does anybody have any questions with getting this function? Guess it's not really a function because it's got too many variables, but this equation. Okay, so we can't differentiate yet because we have too many independent variables. We are going to have to use the equation of constraint, and it said that 200 square feet, boy, this is a tiny, tiny little hall. 200 equals LW. I'm going to get rid of L. It doesn't matter. 2W plus 4 times L. Well, L is 200 over W from the equation of constraint. So the perimeter, which is not really perimeter because it's got that extra 3 in it, but the weighted perimeter, which represents the cost in some way, is 2W plus 800 W to the negative 1. And finishing this is really, you should know how to finish this, but we're going to go through it together. dP dW will equal 2 minus 800 W to the negative 2. I can take out a 2W to the negative 2 and be left with W squared minus 400. That worked out nice. So dP dW equals 2 times W plus 20 times W minus 20 over W squared. 3 critical numbers, 0, I don't think so. Negative 20, not a chance. The only critical number that's in our domain, which really means the only critical number that makes sense, is that W has to be 20. Now that we've understood what the critical number is that leads to the solution, again, we go back to the problem, because you have to read the problem. It could be asking what's the cost, or what's the length, or what's the width. It says what dimensions will maximize the cost. Well, we decided that, I think I can erase all this now. If you want to look at it, watch the video and pause it at that point. We've determined that the width, which was originally this dimension here, is 20. So it's 20 by 10. Why do I know it's 20 by 10? Because the area has to be 200 square feet. So area equals length times width. That means 200 has to equal length times width. So I don't know if you recall, but at the beginning I said, I don't know if I'm drawing this right. I said the lake is over here. And I really couldn't remember. I suspected that it would be the short side of the room that would be facing the lake, which to me is just intuitive because it's the side facing the lake that costs more money. So the rectangle, would look like this instead. And I believe that should be L. I wrote W, but it's L. Any questions with that final example, everyone? All right, as I had said yesterday, and I may have said again today, I'm not going to move on today. I think we need time to practice these problems. So if there are some problems from yesterday's assigned list that you haven't completed, you need to complete those. These are the numbers typed out in your unit handout. I've got, challenges may be a little severe. I've got other problems here that, again, thinking of you in post-secondary, you might have a 50-minute or an 80-minute lecture, depending on what day of the week it is, in your calculus class where your calculus prof teaches you max mins. And then they say, okay, do questions 1 to 40. Or you should know how to do 1 to 40. These ones are going to be in there. Stuff like this is going to be in here. Some of them are quite challenging. I'll tell you that right now. I believe 20 is an incredibly challenging one. And I think it's 15 or 14, the one where you cut a wire, is incredibly challenging as well. But if you feel up for it, you can try those. Make sure you know how to do the basic ones first, which are these. And I think you should be here till at least 2:30 today. If you're here till 2:30, then you get marked present for both periods. I'm not going to worry about if you're here after 2:30. So I'll mute my mic. I just have a couple of quick things to do on my computer, get the recording set up for YouTube, and then let me know when you need help, okay?